So is there something going on between the x variables? Well, if we look at the scatter plot between median income and the number of competitors within half a kilometer, then we see this positive trend, right? The more competitors, the more median income, or the more median income, the more competitors. Okay, and you can make the correlation matrix. Let's see, correlation matrix, and matrix is just like a way to order numbers. So, and it's just this table, okay? This is a two-dimensional matrix, and you just put numbers into it. So that's a matrix. Okay, so you run this code, correlate sales on median income and number of competitors, and you see the correlation matrix here gives you the correlation between these three variables. And of course, sales per square meters is perfectly correlated with itself, right? Sales per square meters. And of course, you see that the correlation matrix doesn't handle names above 8 characters very well, so it kind of shrinks the name here, but you get the drift. Okay, so what's interesting is the median income versus the number of competitors, okay, which you find here. This is the correlation between median income and number of competitors, and it's positive, which means that in more affluent areas there will be more stores or more cafes, which increases the number of competitors. So this is just the correlation between median income and the number of competitors. Okay, so what does this have to do with our regression? For example, if you regress sales on median income and number of competitors, so this is your y, this is your x1, this is your x2, so now you have two explanatory variables. You see that first of all, the r squared has gone up from the simple regression models. So if we just revert to the simple regression model where you had only sales on median income, then you could explain 50% of the variation in sales by using information from median income alone. And in the other simple regression, where you only have one x variable, then you could explain basically none of the variation in sales per square meter by using the number of competitors the stores are facing. And here, by using both these explanatory variables, we can actually explain more than the sum of the explanatory or the simple regressions could do. So now we can explain almost 60% of the variation in sales per square meter by using these two explanatory variables. And actually something which is really important is that the root MSE, the root mean squared error, which is the standard deviation of the residuals, it's 7,300, and in the first simple regression where we used median income, our root MSE was 8,000, whereas by using the number of competitors, our root mean squared error was 11,000. So which means that our prediction intervals are more narrow, which means that our forecasts are more accurate. Okay, so what does this mean? It means that the intercept is the constant here. It's 6,496, which is an extrapolation, so we won't interpret that much, because if median income is 0 and the number of competitors are also 0, then the model would forecast that you would sell 6,496 per square meter per year, where nobody lives. Okay, so what we turn our attention to is the median income, and this would be the B1 coefficient, and the number of competitors has gotten a negative coefficient. Okay, so and the sample regression line would be sales per square meter estimated, equal to B0, the intercept, or maybe I could just write 6,496.95 plus 85.75 times the median income, plus or negative, actually, minus 2,601.10 times the number of competitors. Okay, so what does this mean? It means that if the median income increases by 1,000 in that area, then you would sell 85.75 kroners more per square meter per year. Okay, and if you get one extra competitor, you would, on average, everything else the same, on average you would sell 2,601 kroners less per square meter per year. Okay, and here you see that another interesting aspect is that the coefficient for median income has a t-value of 9.5, which is significantly different from 0, and the coefficient for the number of competitors is also statistically significantly different from 0, because it has a t-value of -3.78, and which means that it's different from 0 on the negative side. Okay, so and another interesting fact is that the median income, the coefficient on median income is lower, is higher than for the simple regression model, because as we saw that median income and number of competitors, they are positively correlated, which means that the effect from number of competitors on median income was accounted for in the coefficient for median income. I'll show you here. So this 669.56, it includes the effect, the indirect effect from competitors on median income, and then onto the sales per square meters. So, which means that in this simple regression model, we had a lurking variable, a confounding variable. Okay. Let's see, and likewise for the simple regression model, when we regress sales per square meters on number of competitors, this positive coefficient, which was not statistically significantly different from 0, it contains the indirect effect from the median income onto number of competitors. Okay. And what we have here is that we have in both these coefficients, B1 and B2, we have kind of included the effect, or split the effect of median income on sales per square meter and of the number of competitors on sales per square meter. So we know that these coefficients, they are adjusted for the correlation between these two explanatory variables. So that's no longer a problem. Okay. So if we look at the slopes in the multiple regression, then we call these partial slopes. Okay. Because it excludes or controls for the effects of other explanatory variables. So if there is a correlation between the x's, then the multiple regression model accounts for that. Whereas the marginal slope, so partial slope, many x's, and marginal slope, then you have y on 1 x. Okay, then you get the marginal slope, and that's just the explanatory variable in a simple regression. So the marginal slope, it often contains the mixed effect of omitted variables, like lurking variables. So yeah, and the partial slope and the marginal slope, they are only equal if there is a zero correlation between the x's, okay, the x variables. Okay, so if we interpret the partial slopes for our example, then for example, if you have the B1 median income is the x1 and B2 is negative 2,601, and the number of competitors would be the x2, and the B1 here of the slope, the partial slope of 85.75 means that a store in location with 10,000 higher median income has on average 857.5 kroners more in sales. That is only true with the same number of competitors. So this is the change on sales per square meters if you keep every other explanatory variable fixed, okay? And B2 is negative 2,601, means that among stores located in areas with the same median income, each additional competitor reduces sales per square foot by square meter by 2,600. Okay, I think we measure this in meters. Yeah, sales per square meter. So what's going on? Okay, because if you look at income, then increased income increases sales. So you have like a beta 1. If this is x1, this competition is x2, sales would be y. If income increases, then sales would increase. Okay, so that's why you would expect like a positive slope from income on sales. Okay, whereas if you increase the competition, you would expect sales to go down, right? So you would have like a negative slope on the competition variable. Okay, but the correlation between income and competition, more affluent areas brings more stores, which means that there is a positive correlation between income and competition, and the multiple regression model, it estimates these direct effects, whereas the effect between the variables are accounted for, but it's not estimated. Okay, so not estimated. Yeah, in multiple regression model. Okay. So that's why this interaction between the explanatory variables can explain why our marginal slope of competition on sales was positive, whereas the partial slope of competition on sales is actually negative. Okay, so let's see. What if we have a data set of individuals' incomes and demographic information? For each individual, you know yearly income, years of education, and IQ. Okay, so what you have is like this table of data of income and education, years, and IQ. Okay. Okay. So you would like to know the returns to schooling. That is, if years of education increase by 1 year, how much of an increase in income will it cause? Well, and if we just think about that for a second, what's the sign of the slope? Okay, is it positive or negative? Should more education give you more income, or should it not give you more income? Okay, and consider two different models. One, simple regression model in which you regress income in years and education. Okay, so that's our first model. So that would be income, estimated income equals the intercept plus B1 times education in years. And two, multiple regression model in which you regress income on years of education and IQ. Okay, so then we have income and the intercept times B1 times education plus the IQ score you get. Okay. Let's see. In which model will you get a larger estimated return to schooling? Okay, so in which year would this B1 be greater? Wait. Oh, okay, that's a typo. Let's see. B2 times IQ. Okay. And I like to write we can actually make a path diagram of income, and you have an effect on income from the education, and you have an effect on income of IQ. And what would you expect that sign to be? Probably it would be positive, right? More IQ, well, if you're smart, then you make more money. And if you have more education, then you make more money. But there is probably a relationship between education and IQ, and possibly it goes both ways, right? Because the more you read, the more exercise your brain gets, and the smarter you process information, or the faster you process information, the easier it will be for you to read. So if this is a positive relationship, then what would the effect be of omitting the IQ variable on education? Well, probably you would get a bigger B1 coefficient on education in regression 1, because here education is like a basket where you put both the effect of education, which is positive, and the effect of IQ, which is also positive. And since there's a positive correlation between education and IQ, we assume that, then B1 will be bigger. Okay? And next time we are going to, we take this. Path diagrams and the bias of lurking variables. Okay. And so whenever there is any variable that is omitted from the regression that is correlated, typo, with both an x variable or the y, and oh my gosh, lots of typos here. With both an x variable and the y variable, then our estimates will be biased. And it might be okay if we are using regression for forecasting or prediction. Remember that you can use regression for two things. You can use it for explaining. Then you look at the coefficients. Okay. Two uses of regression. One is explaining. Then you want to explain what affects the y variable, okay? What affects, okay, I can write that properly. What affects the y variable? Look at coefficients. Coffee. Okay, I'm writing coffee. I need caffeine. Look at the coefficients. The B's, okay? Or two, you can use it for forecasting. And when you do that, then you don't look at, you compare different models. Okay? And then you usually choose the model which gives you the lowest forecast error, okay? Or prediction interval. So so if we are explaining and we want to look for the causal effects, so this is 1, this is 2, then bias is a problem, because you saw that if we run a simple regression, then the effect of the number of competitors were not different from 0, whereas if we included the omitted variable, the income level, then the median income, then we saw that when we control for the median income, then we see that the number of competitors has a negative effect on the expected sales. So that's quite important to understand, and see you next time.